A good day to everyone. We are now at Unit 8 with the topic Database Normalization. For this lecture, we are going to answer the following question. What is database normalization? How important is the need for a database to be normalized? And how can we normalize a table? Our intended learning outcomes are: why should we normalize a database? When should a database be normalized? And what are the steps in normalizing a database and its table? Now, when we say the word normalization, it is a process for evaluating and correcting table structures to minimize data redundancies, thereby reducing the likelihood of data anomalies. It was developed by IBM researcher E.F. Codd in the 1970s. If you may remember, E.F. Codd is the one that proposed the foundation for the development of the relational databases. Normalization works through a series of stages called normal form. Now, usually, your table will go to the first stage called the first normal form until the second normal form up until the third normal form. Usually, when a table has already gone through the third normal form, it is already sufficient enough to be called that your database or your table is already normalized. However, there are some other forms aside from the third normal form, such as the fourth, the fifth, the sixth, the seventh normal form. It all depends on the need of an organization or the need of your application. Normalization, in a sense, usually split a large table into smaller tables. And we define the relationship that exists between those particular table in order for them to have clarity in organizing data. Now, the reverse of normalization is called denormalization process, wherein instead of producing a higher normal form, we are producing a lower normal form. So that is, for example, a third normal form will be converted to a second normal form through denormalization. However, the price you pay for increased performance through denormalization is greater data redundancy. So let us be clear. If you normalize a table, basically you are reducing data redundancy. However, the higher the normal form of a table, the less performance it has. Whereas the lower the normal form of a particular table, the greater the performance it has. So there are setbacks in normalizing a form. That's why usually normalization only takes place up until the second to the third normal form. Always remember that. Okay. There is what we call a prime attribute and a non-key attribute when we are pertaining to columns of a particular table. Okay, let's try to look at this two table and let us try to know what is the prime attribute and what is the non-key attribute. Basically, according to the definition, prime attributes are any attributes that is at least part of a key. Basically, when we say prime attribute, we are also referring to the primary key, wherein it is a column or a group of columns wherein wherein it can define or it can give us the value of the other column just by looking at this particular column. So through the use of a prime attribute or a primary key, we can define the value of a column or a multiple number of columns. Whereas a non-key attribute is any attribute that is described by the primary key or the prime attribute. Basically, this non-key attribute are the columns that are being described by the primary key or prime attribute. In our first example, I have here three columns: stud ID, stud name, and student course. Now, what column do you think, or what columns do you think are the prime attributes and what are the non-key attributes? Okay, for this first table, the prime attribute is the student or stud ID. Why? Because stud ID has a unique value. When we say that student ID or stud ID has a value of 1, we can automatically say that the value is stud name, 1 tamad, and stud course is BSIT. Okay, so basically only one particular um, column is needed in order for us to define the other columns. So stud ID is a prime attribute, whereas stud name and stud course are the non-key attribute. How about this table? Okay. In this table, we have stud L name, stud first F name, stud address, and stud course. As you can see, we could actually say that stud L name can be the prime attribute. Why? When we say stud L name is tamad, automatically we can define that the F name is 1, the address is pasolo, and stud course is BSIT. As well as if we say that if stud L name is Koragi, the F name is Sarah, and address is pasolo, and the course is BSIT. Okay, that is correct. You can say that stud L name is the prime attribute. However, what happens if, for example, there is another person with a last name of Tamad, but this time his F name is, hmm, let's say, Mike. Okay, and then the address is Lawa. The course is PSIT. Can we still say that stud L name is the prime attribute? Of course not. Why? Because stud L name tamad now exists in two rows, and we cannot immediately determine if that particular L name tamad pertains to Juan or to Mike. Now, in order for us to have an exact prime attribute or primary key, what we do is to combine the value of L name and F name. So for example, tamad Juan, okay, this will serve as the prime attribute. These two columns will serve as the prime attribute. And if we combine these two, we will have a unique column or unique value that can define the meaning of the other column. Let's say, for example, I say that tamad Juan is the primary key. Then the address is Pasolo, BSIT. If I say Tamad Mike is the primary key, I can say that the address is Lawa and BSIT. So basically, a primary key or a prime attribute can be one or more columns, as long as it can define the other non-key attributes properly. Okay? Do not forget that particular concept. A primary key can be one or more column that can define other columns. Now, what are the objectives of normalization? First one is each table represents a single subject. For example, a course table will only contain data that directly pertain to courses. Similarly, a student table will contain only student data. Next, no data will be unnecessarily stored in more than one table in order to have minimum controlled redundancy. It is to ensure that the data are updated in only one place. Next, all non-prime attributes in a table are dependent on the primary key, the entire primary key and nothing but the primary key. It is in order to ensure that the data are uniquely identifiable by a primary key value. Then lastly, each table is void of insertion, update, or deletion anomaly in order to ensure the integrity and consistency of the data. Now, when we are dealing with normalization, there is also the concept what uh, called functional dependency, partial dependency, and transitive dependency. Okay. Now, partial and transitive dependency are under functional dependency. Now, what is functional dependency or functional dependence? Functional dependence, attribute B is fully functionally dependent on attribute A if each value of A determines one and only one value of B. For example, the column project num functionally determines, this is the symbol for functionally determines, an arrow sign pointing to the right, project name. So project num functionally determines project name. Okay. In this case, the attribute project num is known as the determinant attribute and the attribute project name is known as the dependent attribute. Okay, basically, the attribute project num is known as the determinant attribute. We could also consider this as the primary key attribute or the prime attribute, whereas project name is known as the non-key attribute or the dependent attribute. Now, when it comes to functional dependency or functional dependence, there are two types, as I have said, partial and transitive. Okay. When we say partial dependency, we are referring to it exists when there is a functional dependence in which the determinant is only part of the primary key. Okay. For example, if A and B functionally determine C and D, and B functionally determines C, and A and B is the primary key, then the functional dependence B function determines C is a partial dependency because only part of the primary key, which is B, is needed to determine the value of C. Partial dependency tends to be rather straightforward and easy to identify. Now, partial dependency from the word partial. Okay, in this example, our primary key is columns A and B. Okay, columns A and B determines the value of C and D. However, column B can functionally determine the value of C. Because B is a part of our primary key, AB, we can say that B functionally determines C is a partial dependency because B is only a part of our primary key AB. Okay, that is why it is called as partial dependency. When we say transitive dependency, on the other hand, okay, it happens because one column is a transit or a road or a means of accessing the value of another column. For example, it exists when there are functional dependencies such that X functionally determines Y, Y functionally determines Z, and X is the primary key. In that case, the dependency X determines or functionally determines Z is a transitive dependency because X determines the value of Z via Y. It occurs only when a functional dependence exists among non-prime attributes. In the previous example, the actual transitive dependency is X functionally determines Z. However, the dependency Y functionally determines Z signals that a transitive dependency exists. Okay. Hence, throughout the discussion of the normalization process, the existence of functional dependence among non-prime attributes will be considered as a sign of transitive dependency. Okay. So always remember that when one or more particular column that is considered as a primary key determines a non-key attribute and that non-key attribute determines another non-key attribute, okay, transitive dependency occurs. Okay. So let us recap. Partial dependency happens when one part of the primary key determines a non-key attribute. Okay, that is partial dependency. A transitive dependency happens when a primary key determines a non-key attribute and that non-key attribute determines another non-key attribute. Okay, repeating group. The term the repeating group derives its name from the fact that a group of multiple entries of the same type can exist for any single key attribute occurrence. We will see an example of a repeating group later on. Okay, the steps for normalizing a table or a database. The term first normal form or 1NF describes the tabular format in which all of the key attributes are defined. There are no repeating groups. In other words, each row or column intersection contains one and only one value and not a set of values. And all attributes are dependent on the primary key. In the first normal form, each column is unique. Okay, we have here under figure 8.1 an ordinary or a table that has not undergone the normalization process. We have three columns, employee, age, and department. Okay. Notice that in our department, we can see that it contains one column or one particular row contains two data, marketing and sales. Okay. If we are to make this table into a normalized first normal form table, okay, look at figure 8.2. Okay, what did we do? What we did was to separate the department into a separate column. So Melvin will now have a department for marketing as well as a new row for sales. Okay. So that is the first normal form. First normal form should be there are no repeating groups and all attributes are dependent on the primary key and all of the key attributes are defined. Okay, so that is the first normal form. We looked for a particular column wherein there are multiple datas contained in one particular column. So we split that into a separate row. Next, the second normal form. The problem with the first normal form is that they sometimes contain partial dependency. Okay. Second normal form has the following steps. Make new tables to eliminate partial dependency and reassign corresponding attributes to the respective table. Now, in the second normal form, we can only do it if the table are already in the first normal form. We cannot skip. If the table is not in the first normal form, we cannot go to the second normal form yet. Okay. The entity should be considered already in the first normal form, and all attributes within the entity should depend solely on the unique identifier of the entity or the table. We look here at figure 8.3, which is the products table. This is already in the first normal form. As you can see, we have three columns: product ID, which is the primary key. We have the product and brand. After the second normal form, what will happen? Okay, because we are in this example, we basically have two particular groups that we need to separate. Okay, because there is partial dependency that exists. Okay, if you take a look at the products table, okay, the brand can be separated from the actual product. Okay, so if we take a look at this products table, it will generate three particular table in order for us to remove the partial dependency. We will produce the product table. You can see it will only contain unique product. A monitor is declared twice. So we will have a product category table wherein monitor is only declared once. Product ID is one. Next, the brand is separated into a separate brands table. Okay. And lastly, we have a product brands table. So the product brands table is basically a lookup table wherein we can find the relationship between the product and the brand. So take note, we have product and we have unique brand. We have four brands, we have three unique product. Okay, and then in order for them to be connected and to have a relationship, we create a new table called the product brands table, which is basically a lookup table for connecting the product to the brand. So this is what it will look like. Okay, so we have product brand ID 1, 2, 3, 4. We have product ID 1, which is what? The monitor. Product ID 2, which is scanner. And 3, which is headphone. We also have brand 1, 2, 3, 4. Brand 1 is Apple. Brand 2 is Samsung. Brand 3 is HP. And brand 4 is JBL. Now, the second normal form, if we are to make a class diagram of the second normal form, okay, this is how it will look like. Okay, we have products, we have brand, and then they are interconnected using one table called products brand table. Using the primary key, okay, we can connect them to the products brand table. Okay, next is the third normal form. Now, before you process your table into the third normal form, should already be in the second normal form. Okay, and no column entry should be dependent on any other entry other than the key or primary key for the table. If such an entity exists, we move it to a new table, and after that we achieve the third normal form. Once we achieve the third normal form, the database is considered as normalized. The third normal form has the following steps: make new tables to eliminate transitive dependency and assign corresponding attributes to the respective tables. Okay. Later on, we will have an example of a third normal form, because in this example, we only process the first and the second normal form. We also have had other normal forms. We have the voice code normal form, which is considered as a 3.5 normal form, or BCNF normal form. We have the fourth normal form, fifth normal form, sixth normal form, etc., etc. Okay, so we will not have examples of this because they are already very advanced and very complicated. Always remember that once you achieve the third normal form, that is already sufficient for your everyday applications and processing needs. Improving the database design. In order for us to improve the database design, we need to take note of the following. We evaluate the primary key. We evaluate the naming conventions. We refine the atomicity. Okay. We refine the attribute atomicity. We identify new attributes as well as new relationship. We refine the primary keys. Okay. We maintain historical accuracy, and we evaluate derived attributes. Okay, we have another example here. This is the sales staff table. Okay. The first thing to notice in this table serves many purposes. Identify the organization's salespeople, listing the sales office and phone numbers, associating a salesperson with a sales office, and showing each salesperson's customer. Data duplication and modification anomalies. Notice that each salesperson, we have listed both the sales office and the office number. There are duplicate salesperson data. Duplicated information presents two problems: increases storage and decreased performance, becomes more difficult to maintain data changes. Okay. So if we take a look at this particular example, sales office Chicago and their office number is repeated. Okay. And then if we look at the customer, they are separated into three columns. What will happen if there is a fourth customer or a fifth customer? Where would we place them? Consider the following. If we move Chicago office to Evanston, Illinois, to properly reflect this in our table, we need to update the entries of all the salesperson currently in Chicago. Our table is a small example, but you can see if it were a larger table, that potentially could involve hundreds of updates. This situation are modification anomalies. Database normalization fixes them. There are three modification anomalies that can occur. It could be an insert anomaly. Okay, there are facts we cannot record until we know information for the entire row. In our example, we cannot record a new sales office until we know the salesperson, because in order to create the record, we need to provide the primary key. In our case, the primary key is the employee ID. We can also have update anomaly. In this case, we have the same information in several rows. For instance, if the office number changes, there are multiple updates that need to be made. If we don't update all rows, then inconsistencies will appear. Okay, if we update the office number for a particular office, all the instances of that office should also be updated. And then lastly, we have deletion anomaly. Deletion of a row causes removal of more than one set of facts. For example, if John Hunt retires, then deleting the row causes us to lose information about the New York office as well as all the customers, okay, that is under John Hunt. Search and sort issues. The last reason we'll consider is making it easier to search and sort your data. In the sales tab table, if you want to search for a specific customer, you would write the query, okay, where customer 1 is equals to, or customer 2 is equals to, or customer 3 is equals to. Clearly, if the customer was somehow in one column, our query would be simpler. Okay. Our current table makes this tough. You would have to use three separate union queries. You can eliminate or reduce these anomalies by separating the data into different tables in order to put the data into tables serving a single purpose. Okay. So basically, from this particular table, we will now process it into a normalized table. Okay. So let us try to review the different steps, but this time applying those steps in the previous table that we have earlier discussed. 1NF or first normal form. When a table is in its first normal form, searching, filtering, and sorting information is easier. The rules to satisfy the first normal form are: the table stores information in rows and columns where one or more columns called the primary key uniquely identify each row. Next, each column contains atomic values and should be not repeating groups of columns. Tables cannot contain subcolumns in the first normal form. That is, you cannot list multiple cities or values in one column and separate them with a semicolon or with a comma. When a value is atomic, the values cannot be further subdivided. For example, the value Chicago is atomic, whereas Chicago, semicolon, Los Angeles, semicolon, New York is not. Related to this requirement is the concept that the table should not contain repeating groups of columns such as customer 1 name, customer 2 name, and customer 3 name. So the issues that we found in the sales staff table are: you are repeating groups for the customer name. Okay. Once recurring customer columns are put into your own table, our example table is converted into its first normal form. So from the sales tab table, we must split them into two. The first table is a sales staff information wherein we will place the employee ID, salesperson, sales office, and office number. And then the next table is the customer table wherein there is customer ID, employee ID, which is a foreign key of the employee ID in the sales staff information, customer name, customer city, and customer postal code. The repeated column groups in the customer table are now linked to the employee ID foreign key. A foreign key is a value that matches the primary key of another table. In this case, the customer table contains the corresponding employee ID for the sales staff information row. Here is our data in the first normal form. Okay, primary key, employee ID. Basically, we separated the sales staff or the salesperson, the sales office, and the office number. We separated the customer table. We created a customer ID field. Okay. We also separated all the customer name. We provided an employee ID in order for us to link the customer to the employee. And then there's also customer city and postal code. This design is superior to our original table in several ways. The original design limited each sales staff information entry to three customers. In the new design, the number of customers associated to each design is practically unlimited. You could add whatever number of customers you have to the sales staff information table. The customer, which is our original data, is nearly impossible to sort. Okay. Number three, the same holds true for filtering on the customer table. Number four, the insert and delete anomalies for customer have been eliminated. You can delete all the customer for a salesperson without having to delete the entire sales staff information row. However, update anomalies remain in both tables, but these are fixed once we reorganize them to the second normal form. I like to think that the reason we place tables in the second normal form is to narrow them to a single purpose. Doing so brings clarity to the database design, making it easier for us to describe and use a table and tends to eliminate modification or update anomalies. This stems from the primary key identifying the main topic at hand and the column serving to add meaning through descriptive attributes. An employee ID isn't much on its own, but add a name, height, hair color, age, and now you're starting to describe a real person. So what is the definition of a second normal form? A table is in its second normal form if number one, a table is in the first normal form and all the non-key columns are dependent on the table's primary key. Let us remember that the primary key provides a means to uniquely identify each row in a table. When we talk about columns depending on the primary key, we mean that in order to find a particular value, such as what color is Chris's hair, you would have first you would first have to know the primary key value, such as an employee ID, to look up the answer. Once you identify a table's purpose, then look at the table's column and ask yourself, does this column serve to describe what the primary key identifies? If your answer is yes, then the column is dependent on the primary key and belongs in the table. If the answer is no, then the column should be moved to a different table. When all the columns relate to the primary key, they naturally share a common purpose, such as describing an employee. Issues with our example data model. The first issue is that the sales staff information table has two columns which aren't dependent on the employee ID. Though they are used to describe which office the salesperson is based out of, the sales office and office number columns themselves don't serve to describe who the employee is, meaning that there is problem guys with the sales office and the office number because they are not actually related to the actual sales staff. Okay. The second issue is that there are several attributes which don't completely rely on the entire customer table primary key. For a given customer, it doesn't make sense that you should have to know both the customer ID and employee ID to find the customer. It stands to reason you should only need to know the customer ID. Given this, the customer table isn't in second normal form as there are other columns or as there are columns that are not dependent on the full primary key, which should be moved to another table. The issues are highlighted for the sales staff information. The sales office and the office numbers are not dependent on the employee ID. And then for the customer table, customer name, customer city, and customer postal code aren't dependent on the full primary key, which is the employee ID. Okay. Employee ID and customer ID are basically the uh, primary key or the prime key attribute of the customer table, not just the customer ID. Okay, both the customer ID and the employee ID. How do we fix the said issue? In the case of sales office and office number, a sales office was created. Okay, so we will create a new table called sales office that will contain the sales office name and the office number. A foreign key was then added to the sales staff information so we can still describe in which office a salesperson is based. Okay, so let us take a look. So the sales staff information has employee ID, salesperson, and a new foreign key called the sales office ID, which is from the new table that we have created called the sales office. The sales office will have an sales office ID, and we will move the sales office and office number here. Okay, in order for us to identify the particular sales office and office number, we will just link the sales office ID to the sales office ID, which is a foreign key of the sales staff information table. The changes to make customer to the second normal form are a little trickier. Rather than move the offending columns to a new table, recognize that the issue is the employee ID. The three columns don't depend on this part of the key. Really, this table is trying to serve two purposes: to indicate which customers are called upon by each employee and to identify the customers and their location. For the moment, remove employee ID from the table. Okay. So from the customer table, we will remove the employee ID, leaving only the customer ID, which will now identify the customer name, city, and the postal code. Now let's create a table called sales tab customer to describe which customer a salesperson calls upon. This table has two columns, customer ID and employee ID. Together, they form a primary key. Separately, they are foreign keys to the customer and sales tab information tables respectively. So what we did is to create a new table called sales tab customer, which will contain two foreign keys: the customer ID, which will link the customer table, and the employee ID, which will link the sales staff information table. To better visualize this, here are the tables with the data. So we have here the customer table. As you can see, all the columns, all the non-key attributes are dependent on the customer ID, which is the prime attribute. As you review the data in the tables, notice that the redundancy is mostly eliminated. Okay, if we take a look, all the customers are unique already. Also, if you can find any update, insert, or delete anomalies, those two are gone. So the anomalies that we have encountered earlier are now gone. You can now eliminate all the salespeople yet retain customer records. So we can delete the sales tab information without affecting the customer record. Also, if all the sales office is closed, it doesn't mean you have to delete the records containing the sales people. Okay, so we don't have to have any anomalies. The sales tab customer table is a strange one. It's just all keys. Okay, with this one, it only contains two primary keys. This type of table is called an intersection table. It is useful when you need to model a many-to-many relationship. Each column is a foreign key. If you look at the data model, you'll notice that there is a one-to-many relationship to this table from sales staff information and another from customer. In effect, the tables allows you to bridge the two tables together. Okay. So looking at this figure, we have sales staff information and sales office. Notice all of this table only pertain to their respective information. The sales staff information only refers to the sales staff. Sales office only refers to the particular sales office. 3 out of 4 tables are even in the third normal form, but there is one table which still has a minor issue preventing it from being so. Once a table is in the second normal form, we are guaranteed that every column is dependent on the primary key or serve a single purpose. But what about relationship among the columns? Could there be dependency between columns that could cause an inconsistency? A table containing both columns for an employee's age and birth is spelling trouble. There lurks an opportunity for a data inconsistency. How can they be addressed? They can be addressed by using the third normal form. In the third normal form, a table in the third normal form should be in first. It should be in the second normal form, and then contains only columns that are non-transitively dependent on the primary key. Okay, what does it mean? Okay, we will go back to the transitive dependency that we have discussed earlier. As I have said, transitive dependency has two types: the partial uh, sorry, as I have said, there are two types of dependency: the partial dependency and the transitive dependency. Okay, so let us take a look. When something is transitive, then a meaning or relationship is the same in the middle as it is across the whole. If it helps, think of the prefix trans as meaning across. When something is transitive, then if something applies from the beginning to the end, it also applies from the middle to the end. Since 10 is greater than 5 and 5 is greater than 3, you can infer that 10 is greater than 3. In this case, in this case, the greater than comparison is transitive. In general, if A is greater than B and B is greater than C, then it follows that A is greater than C. Dependence. An object has a dependence on another object when it relies upon it. In the case of databases, when we say that a column has a dependence on another column, we mean that the value can be derived from the other. For example, my age is dependent on my birthday. Dependence plays an important role in the definition of the second normal form. Transitive dependence. Now let's put the two words together to formulate a meaning for transitive dependence that we can understand and use for our database column. I think it is simplest to think of transitive dependence to mean a column's value relies upon another column through a second intermediate column. As I have said earlier in our example, if A functionally determines B and B functionally determines C, therefore A is transitive dependency of C because we can access C through A. Okay. Consider 3 columns: author, nationality, author, and book. Column values for author, nationality, and author rely on the book. Once the book is known, you can find out the author or the author nationality. But also notice that the author nationality relies upon author. That is, once you know the author, you can determine their nationality. In this sense, the author nationality relies upon book via author. That is transitive dependence. This can be generalized as being 3 columns: A, B, and PK. If the value of A relies on PK and B relies on PK and A also relies on B, then you can say that A relies on PK through B. That is A transitively dependent on PK. Example, person ID, first name, last name. Transitive dependence. No, in Western cultures, a person's last name is based on their father's last name, whereas their first name is given to them. Okay. Person ID, mass index is overweight. Yes. Why? We can tell if someone is overweight through the use of body mass index. BMI over 25 is considered overweight. It wouldn't make sense to have a value is overweight be true when the body mass index was less than 25. Person ID, weight, and sex. No, there is no direct link between the weight of a person and their sex. Vehicle ID, model, manufacturer. Yes, manufacturer makes specific models. For instance, Ford creates the Fiesta, whereas Toyota creates the Camry. To be non-transitively dependent, that means all of the columns are dependent on the primary key and no other columns in the table. So how do we convert our example earlier to a third normal form? So we must remove the transitive dependency. Okay. Customer city relies on customer postal code, which relies on customer ID. So in our customer table, you can see that customer city relies on the postal code, which in turn relies on the customer ID. Generally speaking, a postal code applies to only one city. Although all the columns are dependent on the primary key, customer ID, there is an opportunity for an update anomaly as you could update the customer postal code without making a corresponding update to the customer city. So therefore, if we take a look at it, we can remove the customer city and the customer postal code and transfer them to another table because basically they are not actually related to the customer ID. And if we will not do this, there might be an update anomaly that could occur. So how do we fix the model to the third normal form standards? In order for our model to be in the third normal form, we need to remove the transitive dependency, as I have stated. Customer city relies on customer postal code, which relies on the customer ID. It is okay that the customer postal code relies on customer ID. However, we break the third normal form by including customer city in the table. To fix this, we'll create a new table called postal code, which includes postal code as the primary key and city as its column. The customer postal code remains in the customer table. The customer postal code can then be designated as a foreign key. In this way, through the relation, the city and postal code is still known for each customer. In addition, we eliminated the update anomaly. So what we did is to remove, okay, is to remove the postal code and the customer city and to create a new table for them. After doing that, we will place the postal code as a foreign key on the customer table so that we can still create a relationship between the two table. So to better visualize, here are the customer and the postal codes with data. So as you can see, we removed the postal code. We created a new column called customer postal code, which is a foreign key that will connect to a new table called postal code table having postal code and city. After doing this, we have now eliminated the transitive dependency. At this point, our data model fulfills the requirements for the third normal form. For most practical purposes, this is usually sufficient. However, there are cases when even further data model refinements can take place. As I have said, there are even 3.5 normal form, fourth, fifth, sixth, maybe even seven normal form.